So I would like to first thank the organizers, especially Christina, for putting this working group together and for the invitation to speak. And so I'm scheduled to talk about the stability of a positive mass theorem, but I will start with a basic question in differential geometry. Think about if we have a two-dimensional surface in R3, and say the two-dimensional surface it has positive Gauss curvature. So the Gauss curvature is just the product of those principal curvatures. And then a simple algebra just tell you the surface, even just piece of it, is convex in the sense both principal curvature have the same sign of strictly positive. But now if we raise the question whether we can list to just inequalities, just weak inequality, is the result still holds? So this will be weakly convex. And simple example tells you it's not the case, just because if we look at, say, a plane, right, just a two-dimensional plane in R3, and then we can bend just in one direction. So you can see in one direction it's always flat, but the other direction, the principal curvature can go up and down, can be from positive to negative. The product is always 0, but the surface is not convex. So definitely, probably you require some more global information, and that's the result of a classical result of Chen and Lashoff in 57. They prove if M, the surface is closed without boundary. And so that's a global information. It has no boundary, and it's bounded. And with Gauss curvature non-negative, and it's weakly convex. Okay. And at the same time, they are also interesting in understanding the higher dimensional case. And there are many ways to generalize Gauss curvature to higher dimensions. They actually show at that time, they are interesting so-called Gauss-Kronecker curvature, and which is in higher dimension for the hypersurface in, say, Rn plus 1, and that was just the product of all the principal curvature. But then they actually show it's not true for the Gauss-Kronecker curvature in higher dimension. So under the same condition, closed, even embedded. All right, so the product is greater or equal to 0, but it's not convex. Or is not weakly convex. Gauss-Kronecker is the product. That's right. That's a product of all the n principal curvatures. And they quiz the examples and compute the Gauss-Kronecker curvature has a sign, but it's not convex. So the example is actually quite visible. So we're looking at in Rn plus 1. So this horizontal plane is all other n minus 1 direction. Okay, and I think they consider the case whether n is even or odd. So I will just talk about when the case n is odd. So the dimension n is odd of the hypersurface, and then they look a circle. This is just S1. with the center of the origin and with radius 1. And then they start rotate around the n+1 axis. So what you get is it's not topologically a sphere.
The question, if you can make this example of topological sphere.
Right. It's not clear. It's not. But that's a good question to ask. Right. Probably there's a chance because they actually in their paper they prove on the sound condition of the Gauss map. I think if a Gauss map is degree 1, I think the proof can show the Gauss-Kronecker curvature with a sign will be. I think there's a chance too. I think. Right. It's possible to see from their proof, but at least they did not state that way. They did not state. The question whether if it's a topological sphere and with this condition is weakly mean convex. But it's possible to see from their proof because they have some quite detailed equivalent conditions between a surface being a weakly convex to other equivalent conditions, right? So the proof use Gauss map, and I think if you know the Gauss map has degree 1. And probably that's true.
No, but of course, you always have degree 1 for spherical hypersurface.
Right.
But if you cannot make this Jacobian everywhere positive or negative, it's not
Mm-hmm. So then they just rotate this one, and definitely this is not a convex surface. But then they can choose. There's a range of the center, which you can make the Gauss-Kronecker curvature to be non-negative. But this is just one way to generalize Gauss curvature into higher dimension. There's another possible generalization called the case mean curvature. Right, so instead of taking all the product of the principal curvatures, how about just take some product of them and make a homogeneous polynomial in those lambda i's. So let's call the case mean curvature, which I denote by sigma k. Okay. So it does recover some well-known curvatures. When k is 1, what you get is just a summation of principal curvature, which is the mean curvature. And when k is 2, that's the scalar curvature. And then you can talk about all different degrees of k. And when k equals n, that's the Gauss-Kronecker curvature. So Huisken and Sinetari, I think it's 99. They observe also a direct algebraic fact. So if you have a hypersurface, or maybe just a piece of it, so it's a local result. So if those case mean curvature, one of it is positive, and then you know all the case mean curvature of lower degrees will be positive.
No, come on, that's probably goes to the 18th century.
Right, so I think these people refer. Right, yes, I think that's definitely, in fact, this goes back to Hadamard in 19, well, I mean,
no,
but.
This theorem is not mathematics, it's obvious, but it's geometric theorem. This is algebraic property, which is classical. And it is taken back in by Buba inequality. I remember all the inequalities between symmetric functions are explicitly known. All linear combinations know which are positive, which are negative.
That's right. So it's actually a simple fact. So probably I should not credit them, but I want to credit them with the following question. So the conjecture would be, can this be weakened to weak inequality? Or the question they raised. Probably the ancient people did not ask this question. Right, and now, yes, so we also know it's not true locally, so we need to add it for closed surface. All right, and so it turns out we found the example of Chen-Lashoff does give counterexample to some of the case. So just by working out the same example but choose the center of in some range, we can make the case mean curvature to be non-negative, but the mean curvature always changes sign. So in particular, the sigma 1 does not have a sign. But we are only able to do that for k greater or equal to 3. So probably let me first state. So this was a work with Damon Wu.
Sorry, finally, why did you credit them?
Credit them for giving this question, conjecturalist statement. Right. And we tried very hard. We could not go the example down to k equals 2. And remember what k is 2. K equal 2 means that's a scalar curvature. And let me restate what the case for k equals 2. So that means it's a closed surface in Rn plus 1, a hypersurface in Rn plus 1. If the scalar curvature is greater or equal to 0, whether the mean curvature is greater or equal to 0. So we tried very hard. We could not find a counterexample. And it turns out we actually proved the conjecture holds for k equals 2. So just make the statement more precise. I think here we are showing is embedded. And also we need the hypersurface to be quite smooth. Okay, so what's difference in sigma 2 other than higher degree of mean curvature? So for scalar curvature, this is proven. Yes. And so what's special about scalar curvature? So there is a Gauss equation which we can relate the ambient curvature of which is flat in the Euclidean space, and also the hypersurface geometry by the following way. And here H is the mean curvature. And A is the second fundamental form. And R is the scalar curvature of, this is of N. And there's supposed to be, there's also additional term of the ambient curvature of Euclidean space, which are 0. And suppose we now assume the condition the scalar curvature is greater or equal to 0.
So it's embedded or immersed?
Embedded. Our argument only works for embedded, right? But the Chen-Lashoff, they work for immersed, so they actually show it must be embedded.
It's not true for immersed, or? For immersed is unclear.
Our argument only works for embedded.
You don't know what happens for immersed.
I don't know what happened for immersed. Right. Okay. And so the special thing about scalar curvature is because this equation, and how can mean curvature change sign? So if mean curvature goes from positive to negative, it must go through 0. And that will imply it has to go through, become 0 at the point where the second fundamental form vanishes, which is the geodesic point. So we can talk about those points where mean curvature changes sign, and those are those geodesic points. I denote the set to be M0, just the set of geodesic points. Right. So it's special. It's, I think that's one of the fundamental reasons why it's true for scale curvature, but it's not true for a higher degree of mean curvatures. All right, so, and then, so the reason we actually turned out try to prove this statement is because we found that there's a very naive idea that connects to the positive mass theorem. So I'm going to talk about that naive idea, which is not the true proof. So the naive idea comes from we want to understand the set of the geodesic points, M0. And there's a classical result by Sachs-Taylor. So around that time, I think people were interested in convex geometry. So he actually found out the condition, the sectional curvature condition to guarantee the surface has to be convex. But in the paper, he actually analyzed the set of geodesic points. And what he proved is, so we know geodesic points means, roughly speaking, the hypersurface is rather flat, right? So you share the same geodesic as an ambient space, which is just straight line. But he gave a bit more global information about those points. So what he proved, if there's a connected component of M0, then these connected components actually lies in the same hyperplane. So it's somehow flat in the more global sense. All right, and then once we prove that, you can show then the hypersurface N must tangent to the hyperplane there. And it actually close to the hyperplane up to the second order. So in other words, so it's locally graph. So let's call the hyperplane called as P. All right. And N share the same, is tangent to the plane, and also locally as a graph, the height of the graph vanish on M0 plane. So now we can try to describe a connection of this problem to the positive mass theorem. So when we were thinking about this question, we think about what could go wrong. So suppose the mean curvature does change sign. So from positive to negatives. So it has to change sign through M0. But then we know M0 has to lie in the hyperplane. So let me draw this type of picture. So we know the hypersurface N must tangent to a hyperplane somewhere. So let's say here. This is M0.
When the whole hyperplane touching at many points.
Yes.
It's not at one point, everywhere.
It's right. So here is just a schematic picture.
No, but the picture is only at one point, it will be tangent at one point.
Right.
And your picture is not tangent, actually, it's hyperplane.
Right, so I think my plane will go this way. Yeah, the tilt plane, right?
It's not tangent.
Tangent.
If she's transversal.
Okay, I will try to make it flatter.
So hyperplane is they make it a line.
Right. So it will tangent there.
Why in 2 points? Why you
Oh yeah. So this is
only at 1 point? It is tangent at single point. Why would I say?
It's always tangent at a single point, right? But the static result is actually say any connected component, they're tangent to the same hyperplane.
Say it again.
So all the connected components, not only one single point, right, is tangent to the same hyperplane. So it's a bit more global information, right? And here I'm just assuming the picture I draw, this is one connected component. So you tangent to the hyperplane here.
But again, why do you have a solid with isolated points?
It could have isolated points. Right, yeah, but the thing is, so there's some technical detail to overcome, but we can see if we change size, it cannot only change sign at isolated points,
this
right?
hypersurface of division will be actually smooth or what?
Yes, we are showing is Cn plus 1. Right.
No, but this.
The
When
M0.
it vanishes.
Very good. So here I draw, it looks smooth, but it can be really bad. So we only know it's a closed set, and we don't know any structure of it.
It's a dividing set.
Dividing set.
It's
It's also not quite clear. So here I'm just tell you connection, but
something rather messy.
right, yes, it can be really bad. That's true. So we actually have to adapt the argument which work only near some particular point. We don't even know it actually cut the plane in half. Probably you can argue a lot, but we don't know how to do it, right? But there's a quite vague connection to positive mass theorem, which I'm about to finish. So suppose the mean curvature changes size, it changes through M0, but we know by Sachs-Taylor result, it has to tangent to a hyperplane. So then we can just throw away the top portion of it. So we actually, you can think about, we glue the lower portion to a flat plane outside. So we only take this part. And then we know by our curvature condition, the scale curvature is non-negative everywhere, in particular in the lower portion. And the scale curvature is flat, and but it's actually Euclidean flat outside this lower portion. And then from the positive mass theorem, we know this is one example of, well, we will talk about this later, but it could be asymptotically flat in this, and also with non-negative scale curvature. And what's even more is because that's just Euclidean space outside, the mass is 0. So if you remember from Rick's lecture yesterday, it tells you mass 0 imply this has to be flat, Euclidean flat everywhere. So they cannot have this lower portion. But there is some problem to apply the positive mass theorem. So one, the key.
So you use only the proportion by theorem the follow compact perturbation. Yeah, you don't use it asymptotic, only compact perturbation.
Yeah, you can also put that way, exactly. And I don't know how much smooth you require for this region. So one problem we cannot apply the positive mass theorem is because this can be really bad set. We only know M0 is closed set. So as Misha pointed out, we don't really know too much structure of this set. And so if we want to apply positive mass theorem, we have to apply with the case of really low regularity, especially it meet at the nasty corner. But it's not known yet whether this is true. And yeah, and also the matrix, because we know the graph is C2 closed. So the matrix of this is only C1 across M0. Right. And we don't know scalar curvature even is non-negative across the corner in any distribution sense. But in general, I think it's overkill to use positive mass theorem because it's a very special case. We are only talking about hypersurfaces in Euclidean space. So we're looking for probably a simpler proof to the positive mass theorem in Euclidean space. But then we found out work by George Lan, whose thesis on the Hilbert actually prove the positive mass inequality for graph in Euclidean space. And this based on a very neat observation. So he rediscovered the formula. So now we're looking at a function, right? So at least C3. And so we can compute the scalar curvature of the graph. Right, so the picture is, so here, right now I'm not assuming the asymptotic, it's just a general formula. But let's look at a graph of U. So this is a hypersurface. We can compute the scalar curvature. And it turns out the scalar curvature is a divergence quantity. So here, all those subscript I means the partial derivatives. And here we are in Euclidean space, so it's just ordinary partial derivatives. And this is actually a formula, I think.
Fine, because third derivative must cancel off.
Right, so yeah, there's third derivative.
They must cancel off. There is no third derivative.
Okay, so yeah, I think.
No, but they must cancel. In this formula, there are third derivatives.
Right. Yeah, I think you are right. Yeah, so the third derivative will be,
yes,
that's right.
Yes, but they cancel. Gauss formula, you know, they must cancel.
That's right.
So.
Good.
But if you open up the formula, the some terms disappear.
That's real right. Yeah.
It's beautiful, not open.
Yeah.
Yeah, that's the point. But actually rediscovered by, so Lan just rediscovered this formula due to, I think Raleigh, he talked about more general settings. So I think he actually proved all the case mean curvature are divergence of some vector field. So I forgot which.
Divergence form, of course.
Right.
Because Gauss formula in divergence form.
Right, but this is only true in some special circumstances, right? So that's why it makes the general setting of positive mass theorem so hard. But here we're just looking at a graphical case. And then, so if you have a divergence quantity, let's apply divergence theorem. So we integrate, let me write here. So apply divergence theorem, we can integrate over a compact ball. Right? And then for each one, we get the boundary term. And then you let the ball exhaust to all the Rn. So we take limit to infinity. All right. So it turns out this quantity is analogous of the ADM mass in general setting. It actually can be proved that's equal to some constant multiple of the ADM mass.
What is the map there? Which map again?
Which map?
You said you do it. It's multiple
of the ADM mass, which is
ADM mass. Okay.
Yes, right. Yeah, ADM mass. So here, in order to see that, how about let's assume some additional. We assume the grad U goes to 0, so the normal vector becomes vertical toward infinity. So we will take this definition as our, what do I mean, a graph to be asymptotically flat.
You don't need a rate of decay?
Actually, we need a precise decay in order to show it coincides with the the classical ADM mass. But in general, this quantity is always converge, right? Maybe infinity because it's a monotone quantity if we assume non-negative scalar curvature. Because
Could be infinite, though.
could be infinite, that's right. Okay. All right, so then George Lan just give now a two-line proof of the positive mass theorem. So if scalar curvature in the graphical setting, I should finish my sentence. So if scalar curvature is greater or equal to 0, and this quantity is non-negative. And you can also see what happens when mass is 0, which is the case we need, the rigidity case. When mass is 0, what he can get is the graph has to be scalar flat. But it's not quite yet, right? Because we expect a lot to be a Euclidean space, to be just Euclidean flat. But there's also a problem, right? Because you have so many ways to put the Euclidean space into a codimension 1 Euclidean space just by bending in one direction, the similar picture I show you. And all of those has 0 sectional curvature, so it's Euclidean is isometric to Euclidean space, but they are not really a hyperplane. So the rigidity, what we expect to show is to show the graph is a hyperplane, so U is a constant. But this is not quite saying that yet. Right? So we actually prove the expected rigidity, the graph of U has to be, so U has to be a constant and graph U has to be a hyperplane. But I want to point out there's no general rigidity of scalar flat graph.
In your case, it's not a graph, though, right?
In our case, it's not a graph. That's right. So we are working. Right. So we actually use the same argument to prove both the closed case and also the graphical case. And actually, we only need the hypersurface to be graphical outside compact set in order for the argument, which I have not talked about yet, in order to make it work. But let me.
Yeah, because this formula to everything can be the reason for any hypersurface is still true, right?
It's true locally, definitely, yeah.
No,
Because
but then you integrate, you don't care being graph or no graph. You can rewrite it invariantly and then you have the same formula. You never use the graph for this algebraic identification.
Right. So for this proof, but it does use its graphical everywhere in order to apply the divergence theorem. Even for the whole region, right? If you apply divergence theorem only outside.
No, you still have probably the divergence formula in different coordinates.
In general, it's not divergence, right? Because we can, for example.
But divergence in which coordinates? Divergence.
I think you are right, but in general, it's not. Why Hilbert looking for, he asked the student to do that because he was looking for some divergence structure of scalar curvature, but it's not true in general. Otherwise, if in some coordinate, I think, well, I mean, yes.
Coordinate just say divergence.
In local coordinate, probably you mean.
It's an defined invariant because of divergence of scalar curvature is a basic fact, right? You're right.
So I probably should say you're looking for the a coordinate which defined globally to make a divergence. Otherwise, you only have locally is divergence. But
The divergence is on the base, it's not on the.
Of course, the divergence not of the base, the divergence inside of hypersurface, of course, yeah. You have to write invariant quantity on the hypersurface will differentiate with this. And it is. If it's true in this context, it will be always true.
Right. But if that were true, then possibly you can prove the positive mass theorem for intrinsic manifolds, right? Not sitting in any bigger space.
No, but you use it being locally hypersurface, so identity.
Mm-hmm. Right. Probably, yeah. So I think there's also, I think if you can write down as a invariant quantity on the surface instead of base, I think it will definitely make things, I think, more interesting what means geometrically, right? Because in the following proofs, which on the stability positive mass theorem, we particularly use is graphical everywhere. So we can find a very interesting quantity defined on the level sets, which definitely depend how it's sitting inside the big space. So, but we don't really know. One of the things is we don't know how to generalize those quantities in the invariant way, just define the manifold. Yes. But let me probably talk about example of scalar flat graphs. May not be hyperplane, right? So it comes from the important family of matrix called structural matrix. So this structural matrix can be defined just a matrix on Rn with a ball removed. And the matrix given by in polar coordinate. Right. But because this is rotationally symmetric, so it can be embedded into a codimension 1 Euclidean space.
So it's complete near the boundary of the ball, over the ball.
So it's actually not complete, but there's a way to extend across the boundary.
Keeping the flat.
Keeping the scalar flat, right? So I can draw a picture to show. So if you write down as a graph in Euclidean space, it will become, so this is a function defined. Right? And the graph of U will equal to, how about let's say this. And the function U can be written down explicitly in the exact form in lower dimension. So in dimension 3, it has the exact form. So if you draw the picture of the graph, so it has inner boundary, and at when the base over the base of both radius 2n. All right, and there's also, you can write down this in a closed form in dimension 4, I think is, so let me check. So it's just by solving the ODE. And in high dimension, we don't know what exact closed form is, but we know it goes to asymptotic planar.
But so how you extend along across this pole?
Right. Yes, I will talk about that. Right. So in particular, this boundary, the graph, the gradient of the graph becomes infinity. So which means this is a minima surface inside, and the graph of U. And just by symmetry, you can reflect it across. So you can make a complete scalar flat hypersurface, but which has 2 ends.
It's actually we see infinity.
It see infinity.
It's just a parabola rotating.
Right.
I said like parabola.
Okay. Yeah, that's right, because it's rotationally symmetric.
Infinity.
Yeah, because a lot of derivatives are so no, all derivatives.
That's right. Okay. And also I want to point it out, so if I have chance to talk about the stability, then we'll see this quantity is the ideal mass. And what the stability of positive mass theorem want to understand as the parameter n goes to 0, how the manifold converge to Euclidean space, because we know when n is 0, it has to be Euclidean space. And you can see in this picture, it converges in a way. First, the graph looks more flat. So if you looking at this with the inner boundary, and then as you decrease mass, it becomes more flat. And by the same time, the neck size shrink as well, because it's given by the radius equals to this number. And as m goes to 0, this neck actually just shrinks to a point, so it becomes flat. Okay. So what this example tells you, if you only say scalar flat, whether it's Euclidean space, it's not clear, right? Because we have example which is scalar flat. A graphical outside compact set, but it's not flat. So we definitely need more information. So in fact, in Lan's proof, he actually worked out a case where U is not graphical everywhere. So we can have U, which is only graphical outside compact set. So say this is a compact set of Rn, but we will require the graph, the function u is constant on the boundary. All right. And then you can still apply divergence theorem. So now here. So we can apply divergence theorem where the graph is defined, so it's outside omega, and then you will pick up the flux integral on the boundary, on the inner boundary. Right, so that's exactly the same vector field, but inner product with the, I think here I'm sure is an inward normal vector, point inward. Right, so n is a vector. Okay. But then if we are showing it's a level set, then the normal vector is proportional to the graph f, or the negative, depending on whether the f is increasing or not. So it turns out there's a geometric interpretation of this quantity. So I think this is plus, right? Sorry. So then you have to add another term. If you rewrite the integral, that becomes minus of sigma. And here is mean curvature of the level set in the hyperplane. And you can think about this is a weighted mean curvature with some weight given by the graph u. this is divergence. So the negative divergence. So for a ball with respect to the inward vector, the mean curvature is positive in this convention. So if you work out this quantity, so you will see if you move this term to the other side, you'll find out you can, of course, generalize this argument not only on sigma, but on every level set. So I don't know if you can see purple here, H. And this sigma H is the arbitrary level set of height H. So what you get is actually a quantity which defined on every level set. And if you work it out, because the scale curvature is non-negative, you will see this quantity is actually monotone. It's a monotone quantity and goes to the ADM mass. So in generativity, people like to give a name called quasi-local mass. So this plays a very important role for the proof of rigidity and also for the stability. So let me write a quantity here. So this is a quantity defined on each level set, and it's monotone increasing to the ADM mass. Right? So if we can prove, so if mass is 0, so this quantity equals to the total integral of scalar curvature. And if mass is 0, that tells you this quantity, which has the opposite sign, has to be 0 as well. And that's a quantity defined on each level set. And what we prove is really this quantity, especially the mean curvature, is non-negative. So if the integral of this quantity is 0 and mean curvature is non-negative, then the mean curvature has to be 0. But it cannot be true because we know any bounded closed surface, hypersurface in Euclidean space has a convex point. So that's how the rigidity works. So we will actually say if it's not flat, then we can work out the level set. And then if we prove the level set has non-negative mean curvature, and then we show it actually has to be 0 and not contradict. So we show all right. So it depends on a very basic inequality. I will just write down. So what we do is we really examine the angle between two mean curvature vectors. So here we have a mean curvature vector of the level set sitting in the hyperplane. And then we have a mean curvature of the hypersurface. And then we look at the angle between them. And we see the angle is actually bounded below by the scalar curvature of the graph. So in particular, if scalar curvature is non-negative, the angle will be less than pi half. So it actually has to always point to the same side. That's what we prove essentially. Okay? All right. So I think I will use the last 5 minutes to state at least what the statement of the stability of positive mass theorem. So I want to keep this one. So there are already different versions of positive mass, stability of positive mass theorem. They want to show if you have a sequence of asymptotically flat manifolds, which mass goes to 0, and how the manifold converge to flat space. So in Christina's talk on Monday, you will see those convergence cannot be true everywhere globally if you're looking at the smooth convergence, or if you look at the Gromov-Hausdorff convergence. Because the example just show you it may not converge to Euclidean space in those stronger norm. So Christina and Wenger introduced the idea of intrinsic flat convergence. And then she and Dan Lee actually conjecture cannot be right. Yeah. All right. So there's some condition on the manifold. So suppose the sequence of asymptotically flat manifolds has non-negative scalar curvature, and the masses goes to 0. But then you also have to be careful because the convergence only talk about compact set. So, but we are working on the unbounded manifold. So there is usually some normalization condition. Because if you are working not so carefully, you may pick a compact set, say here in the region, which go further into the asymptotically flat region. And then the convergence becomes trivial, right? Because just by asymptotic flatness. So you have to pick your normalization condition in order to capture what happened inside here, where the larger scalar curvature may happen. So what normalization condition they propose is they look at a special surface, which really probably we don't know what the special surface will be. But then in the conjecture, at least they state we're looking at a surface. So they just state it's a three-dimensional case. So you look at a surface inside with area right? And then you also pick a corresponding surface in the sequence. So we don't really know what lot surface will be, but they normalize the area to be a fixed constant. And then the state under the normalization condition, a neighborhood around those special surfaces would converge. So they say that normalization condition is and they conjecture for so the tubular neighborhood around the special surface with the radius d will converge in the intrinsic flat norm to R3. Okay. So to finish that, I just say there is some progress to prove this conjecture. And so the general form is still open, and I think it's a quite hard problem. But there's some partial progress, and I will stop there. So they first proved in the rotationally symmetric case. And so in particular rotationally symmetric case, oh yeah, there's also another geometric condition. So I think you need to assume there's no closed minima surface. Inside. Okay, and or you can assume either the manifold is complete or there's a boundary. If there's a boundary has to be minimum. So it be in the interior. All right. So and then in the work, so I come in to join work with them. We put for the graphical case. So using the exactly those very important quasi-local mass quantity, we're able to estimate the volume, and which show, especially in higher dimension, the volume has to blow up in finite height, and the height is really determined by the mass. So we show you actually the graph will, in a very strong sense, converge to Euclidean space. The height goes to 0. So there are also some other partial results in, especially Christina lead several teams to work on this problem. So he and Eva Stavrov, they proved a class of conformally flat matrix, the conjecture true. And also Brian Allen, I don't know if he's here yet, but he proved the case assuming the manifold has a smooth foliation by the inverse mean curvature flow. But it's still widely open, and I think there's a lot of interesting phenomenon to discover. Okay, so I think I'll just stop there.